Hello everyone, my name is Shichen Lu. I'm from Jamie Levis Group, which is in University of Pittsburgh, and I'm going to talk about high mobility sketched nanostructures at aluminum oxide and styrene titanium interface. So this work is copied with Lloyd Gordon's group, which is in Harvard University, and Sang Wu Li is the one who helped us grow samples. So I think most people in this session has been familiar with ALL-STL system, which has a 4 unit cell critical thickness, which means if we have 4 or more unit cell ALL on STL, we get a metallic interface. But if we grow less ALL on STL, we get an insulating interface. And this metal insulate transition can be tuned by a backgate. There are many theories can explain this mechanism, and one of them is polar catastrophe, which can explain most of the properties of ALL-STL system. But somehow there's another group of material which are non-polarized. For example, there's a gamma crystalline aluminum oxide on STL, which also shows this metal insulate transition at the interface, and they also do angle dependence of transport management and the angle dependence XPS. They both show the metallic interface is to a 2D electron gas, which the electron confinement is around 1 nanometer. And from the transport management, they found a quantum oscillation, which turns out to be SDH oscillation or Sabanikov-Dehance oscillation. And by do analysis on those oscillations, they can extract the mobilities around 7,000, which is quite high, because for the typical oxide heterostructure, the typical number for the mobility is 1,000. And another group grow amorphous aluminum oxide on STO, and they also get this metal insulated transition. They also think the mechanism to cause this metal insulated transition is the oxygen frequency formed at the interface. Because when you grow aluminum oxide on STO, there are small islands which oxygen frequency will be formed underneath, and when they get circulate, the whole interface will become metallic. And so we copied with the same group, and they grow the samples, which the thickness is in the region of the transition. We use the technique in our lab, which basically we use a FM tip as a top gate to tune the interface, and we can draw or write wire nanowire structures and also wider whole bar structures. So I'm going to show you a video which demonstrates a wider whole bar structure procedure. So basically, we write those virtual electrodes first, which is improve the contact between the structure and the metal electrodes, and then we write the structure in both directions. Here, the main channel we write in horizontal first, and then we write in vertical again, which improves the quality of our structure. So here the channel width is about 500 nanometer, and the channel length is about 3 micron. So here is the whole image of the structure. Okay. The next thing we can do is the measure transport measurement in the this wide whole bar structure first. So we can measure the channel resistance versus field. We found this linear dependence of magnetic resistance, but that's not important thing. The point is we get this quantum oscillation in our structure also, which shows up here. And also we can measure the whole resistance. Basically, we found a linear dependence. So oscillation is not obviously in this whole measurement, but we can do differential analysis, which found the oscillation in channel resistance and the whole resistance are correlated. Then we can do linear fitting and extract the carrier density is about 510 to the 13, and the mobility number. I'm going to talk about this later. So we can do some analysis on those quantum oscillations first. So by doing the measurement on the different backgate and subtract the magnetic resistance background, we can do Fourier transform also oscillation and found the period doesn't change much, and from the period we can calculate the carrier density around 1.3 10 to 12. And from the temperature dependence data, we can do LK formula calculation, which is the standard way to analyze the Sabatnikov-Dehance oscillation. So I'm going to skip the detail of this analysis, and at last we can extract the mobility is around 2.5 10 to the 3. So we have two kinds of analysis. One is whole measurement analysis, and one is Sabatnikov-Dehance oscillation analysis. So the mobility for both analyses are in the same region, but the carrier density are far. So carrier density for whole measurement is is much larger than the carrier density in SDH oscillation analysis. Even we consider the 6-fold degeneracy in STO, which 3 comes from valley degeneracy and 2 comes from spin 1/2. So we multiply this number by 6. It's still smaller, much smaller than the 4.9 10 to the 13. So there might be some inter-subband occupancy which do not contribute to the SDH oscillation, but this theory still needs to be proved by more experiments. Okay, then we try to do measurement in our nanowire structure because we want to improve the mobility performance. Because we already have a paper which talk about the mobility enhancement of the nanowire. So here we shows the solid bulk, shows the bulk structure, which means the width and length is almost the same, and the nanostructure shows here, which has the much longer length, typically several micron, and smaller width, so 10 nanometer. And we found the nanowire mobility is 1 order larger than the bulk structure. So we do this kind of measurement in our nanowire structure too. So we do hole resistance measurement and also the channel resistance measurement. We can extract the mobility and the carrier density. So the mobility actually goes from 200 at room temperature to 3000 and at 20 K. Because this sample is designed to do measurement for temperature dependence, the lead get bad at below 20 K. So we write another structure. Basically, we erase whole structure and write again. Then we cool down the structure directly to 500 millikelvin. And this time we can reach mobility around 9000. And we can still improve this by apply a positive backgate. Basically, we change the distribution of the 2D electron gas. It's not a 2D because it has a 3D distribution along z-axis. So we change this distribution and get high mobility by applying 10-volt backgate. The number is 100,000. So as I said before, the typical number for the mobility in oxide structure is around 1000. So 100,000 is quite large mobility. Okay, here's the summary for today's talk. So first thing, we found 2D electron gas can be found at non-porous material interface. And we found very high mobility in our structure. First proof is the Sabatnikov-Dehance oscillation in our 2D structure. And by decrease the nanowire width down to 10 nanometer, we can get 100,000 mobility. Of course, at a low temperature. Okay, so that's my talk, and thanks for your attention.